All right. Hello, everybody. Sorry I haven't been uploading in a while, but also you might notice this is chapter 5 of, again, classical dynamics of particles. We're skipping chapter 4 because my class doesn't cover it, so I'm just following what my class does because, again, I'm doing this, to help me study. So, without further ado, chapter 5 is gravitation, something you guys have all probably heard about before, and we all like to think about Newton, right? Apple falling on his tree, which I think is a false story. But anyways, so gravitation is going to cover, it's a pretty short chapter, 5 things, or 4 really. The gravitational potential, and we're going to look at some equipotential surfaces, and then we're going to see kind of where to use it, and then a really cool application with the moon and how it causes ocean tides and stuff, and we'll see how it kind of stretches the Earth. So, okay, let's get into the 5.1 Introduction to Gravitation. Okay, so we all know Newton, right? Smart guy, published his book Principia in 1687, and he ended up formulating Newton's law of universal gravitation, which states basically that each particle that has mass attracts all the other particles that have mass. So there's forces between things that have mass. So in mathematical form, we write as the force, which I'll do F sub g, of gravity is equal to negative g, the gravitational constant, m over r squared in the r direction. That's basically telling us, right, if we have two masses, we'll think of these as planets, m and m. If we look at the force of gravity on this one by this one, it's towards it. That's why the negative sign comes from. It's given by this equation, where g is Newton's gravitational constant, is 6.673, plus or minus some stuff, times 10 to the negative 11 newtons per meter squared. Newton times meter squared, whatever you need to make the units work out for it to turn this into a force. But anyways, okay. So they kind of give us a diagram, which is basically what I drew. This is the figure 5.1. Oops, there we go. We see we have the force, right, from this mass onto this mass points this way. And the reason why the negative sign comes in is because from the radial direction, if you draw a radial vector from this to the other one, r is this way, but the force points in the opposite way because it's towards the object. That's kind of the notational convention why there's a negative sign. But okay. But what happens if we have a continuous distribution of matter? In other words, it's not just the point mass of m and big M, right? Well, then we just do what we always do with calculus, is just turn it into an integral form, negative gm. We're assuming little m is still a point mass. And then we just do a volume integral for the big M, which is just given by rho of r prime, er, over r squared dv prime. And that's kind of how you assemble. So, for example, for a sphere, right, what you would do for a sphere is you would kind of just build it with spherical shells outwards. And that'd be like the self-assembly. But that's just the continuous distribution for force of gravity. We're just taking m and turning it into a volume integral. And we can kind of see that in this kind of explanation, where we have a bit more of a complicated object, and if both m and big M have are not point masses, you have to do an integral for both, basically. That's kind of the point. So, okay. And now, another thing you might have seen is you guys might have heard of this variable, g, right? Which we like to think as, 9.81, 10, gravitational acceleration, right, and whatnot. Now, that's all well and good, but what is it actually? So g, right, we go from Newton's second law, F equals ma, right? So then, if a is our acceleration vector, or the gravitational field vector, g is defined as the force over m, which if we plug in our equation from above, this one, we get negative g m over r squared er, where the little m's cancel out, right? Because we had g m over r squared divided up by m's cancel out, right? Okay. In integral form, same thing. We have g is equal to, g is a vector, remember, negative big G volume integral rho of r, just your standard volume integral from the density to get mass. Okay, and this is the gravitational acceleration constant. On Earth, it's 9.8, 9.81, 9.80. Depends on actually where you are, because let's do a little example on the Earth. We know the Earth, right, is a sphere. It's not actually a sphere. It's more, ellipsoid. I don't know what you'd call that. It's like a squashed sphere, kind of like that. And then if you zoom in, right, take a magnifying glass and I zoom in on the Earth, right, we look at the surface of the Earth, we actually have like mountain ranges and stuff, right? So the gravitational constant, like here, for example, is going to be different than like over here, because when you do the volume integral, you have less or more mass and so forth. But to a very good approximation, it's constant across the entire Earth's surface. So, okay, that's enough for the introduction. Let's get into the gravitational potential. So 5.2, gravitational potential. Okay, so we know the gravitational field vector G, right, goes as 1 over r squared, right? Now, this lets us write, then we can basically write G as the gradient of a scalar function, because we have the 1 over r squared dependence. It doesn't vanish. So then G we can redefine as the negative of the gradient gravitational potential. Sorry. And its units are force per unit mass times distance, or energy per unit mass. So let's do energy per unit mass. Okay. And using mathematical equations, we know gradient of phi is basically just the partial derivative in the radial direction, because that's the only way G points, right, radially. So it's Gm over r squared er. Right? Now, what if we integrate to get just the gravitational potential? We get phi is equal to negative Gm over r. Okay? And we're ignoring the, the plus c in this case, because it's arbitrary and we can choose any potential. Because basically a potential isn't defined unless it's a difference between two things, if you remember from our earlier conversations. So constants don't really matter because you can always set something to 0. So yeah. Okay. Now if we look at a continuous distribution of matter, in other words, we're going to change mass again. Distribution, then we just get phi is equal to the exact same thing, G, with our mass integral instead. Where we do the volume integral of the density over R. Now, that can be a little complicated at times, so I kind of hinted at this. If you do, like, for example, like, if mass is distributed over a thin shell, you can do basically a surface integral, where you do the surface density, which they use rho. I learned in other classes to use sigma for surface, use lambda for line, sigma for area / surface density, and then you use rho for volume. But I'll use rho s because they use rho s. And then for a linear case, that's area. Linear, same story for the integral. You just change your, what's it called? You just change your density. So rho linear over r ds. So yeah, I would use lambda there, but same thing. It's all the same math. So, okay. Now, why do we care about this gravitational potential function? Well, we'll see why if we sort of consider the work per unit mass. Because remember I said the units are an energy per unit mass. So let's look at the differential work element, which is given by negative g dot dr, which is just, if we look at g, well, that's just gradient of the gravitational potential dotted into dr. Well, that's just equal to a sum over dummy indices of the potential, which is just equal to the derivative of the gradient potential. And this is because phi is a function only of the coordinates of the point at which it's measured. In other words, phi of x1, x2, x3 only depends on basically its position. Okay, and that basically lets us know then that the amount of work per unit mass that must be done on a body to move from one position to another in a gravitational field is just equal to the difference in potential of these 2 points. That's what this equation right here is saying. Like, the differential work element is just equal to the difference, basically. Well, the derivative, which is the difference, right? So that lets us write the gravitational potential energy then as U is just equal to m phi. Okay, and we then know that the force, right, from chapter 2 is equal to the negative gradient of potential. And we can check and see that it's the same. If you do the math, you should recover negative gmm over r squared er, which you do. So, okay. Let's go over an example now. Example 5.1. Okay, we want the gravitational potential both inside and outside a spherical shell of inner radius b and outer radius a. So, A, B, this is what we care about. Okay. And we basically want to find the gravitational potential inside and outside. So, okay. Immediately, since this is spherical, we have some symmetry. And we can basically calculate the, the d phi angle in spherical coordinates, right? Instantly is just 2 pi. So let's see what that looks like. So let's look at the gravitational potential, right, which is equal to negative g over volume. Remember, we're going to take the density over r dv prime. Okay, and we're going to change dv prime into, dr d theta, or dr sine theta d theta d phi. We do the phi integral. The phi integral is trivial, right? Because since it's spherical, right, you immediately integrate and you get 2 pi. So now we have negative 2 pi. The density comes out because it's a constant. G is still a constant there. And now we have the volume integral. For the r integral, we have from b to a, because a is, remember guys, a is greater than b, of r prime squared dr prime. And then we have the integral from 0 to pi of sine theta over r d theta. And this lets us basically... Oh, and then we can use the law of cosines to simplify this, since r squared is equal to plus r squared minus 2r r cosine theta. And since r is constant, big R, sorry, that is constant, we can differentiate this equation for r prime to get 2r dr is equal to 2r prime r sine theta d theta. So let's kind of look at the entire geometry for this so you can actually see what we're actually integrating over. So you can't see the phi here because the phi goes this way. That's where the factor of 2 pi comes in, and then we're integrating basically over d theta and then dr right here. Okay, So this tells us then, if we look at, oops, I messed up. So sine theta over r d theta is equal to dr r prime r from this equation. And then we can just plug it in, and we get phi is equal to negative 2 pi rho g. Remember, big R is a constant, where big R is just basically the distance to the point you're measuring, because we're just basically evaluating the potential at some random arbitrary point p, a distance big R away. Times integral from b to a of r prime dr prime, and then we go from r min to r max dr. Since we basically changed our theta integral to an r integral, not an r prime integral. So then when phi, where r is greater than a, in other words, like in this drawing, outside of the sphere, we just recover negative 2 pi, let me just rewrite it, g over r, integral b to a r prime dr prime, and then we integrate the minimum r distance, right, is big R minus r prime, maximum is r plus r prime dr, and we do this integral, we recover negative 4 over 3 pi rho g r a cubed minus b cubed. Okay. Now we could just plug in the mass for density. So remember, mass of the shell, so it's a sphere. What's the first sphere, right? We have mass is equal to, or density is equal to mass over volume. So mass is equal to density times volume. Volume is 4/3 pi r squared, right? So that immediately then tells us cubed. Sorry, my math is a little off. So then the mass of basically this right here is the mass of this big sphere minus the mass of this little sphere, right? So that's then mass is equal to 4/3 pi density a cubed minus b cubed, right? So if we plug this into here, right, we now get phi of r greater than a is equal to negative gm over r. And you're like, wait a minute, well, that's just the general equation, and that's exactly right, because that's what we expect to see, right? Now, what if we care about the direction when it's less, like aka inside, like right here, when r is less than b? Well, let's redo our integral, negative 2 pi beta. So the integral is the same, it's just we're integrating from different limits. R integral of b to a r prime dr prime. Again, r minus r, r plus r, dr. We integrate that, we get negative 2 pi rho g a squared minus b squared, which if we compare the two, it's clearly different, right? And it's constant, and notice it doesn't matter where inside the shell it is. In other words, since it doesn't have a dependence of r, here, I can draw on his, it's entirely constant in here. So right here and right here is the same. So these 2 points are the same potential, if that makes sense. So okay, that's all well and good. And then you can also do an integration if you want to find in between. It's a little bit more math, but not really. That's kind of the answer. You basically just change the lower limit of integration for this one right here by our potential, and then you change the upper limit by the potential from the phi r is greater than a. But that's not what the question asks us to do, I don't think. So, okay. Anyways, this example is very important because it allows us to basically get the magnitude of the field vector g for the three regions. So g when r is less than b is equal to 0, right? because we have our phi expression is here. You can't exactly take... if you take the partial derivative of this with respect to r, there's no r value in there, so it goes to 0, right? That's why it's 0. When g of b less than r less than a, you get 4 pi, and I kind of skipped over how to actually get the potential of this. I kind of just put up the answer. It's in the textbook if you want more, but if you take the partial derivative of that, you get this expression. And then the easier one is when r is greater than a, right? We give negative gm over r squared, right? Because we had just gm over r right here. What's the derivative of 1 over r? 1 over r squared, right? Negative, but same thing. So yes. Excellent. Yeah, then they have some graphs about how it varies and stuff. Yeah. Okay. Let's skip those. Okay, let's do one more example because I really like this example. Example 5.2. I think we'll skip 5.3. 5.2 example. It's about how to find the orbital speed, basically. So I could just let me screenshot the question actually because it's kind of long. Astronomical measurements indicate the orbital speed of masses in many spiral galaxies rotating about their centers is approximately constant as a function of distance from the center of the galaxy. As shown in figure 5.5, show that this experimental result is inconsistent with the galaxy having its mass concentrated near the center of the galaxy, and can be explained the mass of the galaxy increases with the distance r. Okay. So this is figure 5.5. I should probably need a text back from someone real quick. Okay. So sorry about that. We can see from here, experimentally, basically from Kepler and Newtonian laws, you expect to get this, and then experimentally you actually get something bigger. Sorry, my girlfriend is texting me, and she's, I don't know, not having the best time. I'm sure it's fine. Anyways, okay, let's solve this problem. So let's find the orbital speed due to the galaxy mass m when it's within the radius big R. Okay, so let's just assume the mass distribution is spherically symmetric to make our calculations easier. In that case, the gravitational force is equal to the centripetal force. In other words, our gravitational force, oops, my pen is not working, gmm over r squared is going to be equal to centripetal equation mv squared over r, right? So we can solve for v. V is equal to square root gm over r. And we notice that if this were the case, we would expect it to have this dashed line, right? Because we see the 1 over square root r dependence, because g and m are constants. So I'm going to rewrite this as alpha square root 1 over r, right? Which is, I guess, 1 over square root r, where alpha is equal to square root gm. And we notice that the experimental data actually does not follow that trend. And therefore, the only thing that can happen is if, in the previous equation, the mass of the galaxy is a linear function of r. So m of r is equal to like alpha r, basically. Yeah. Okay. And they give some explanation that like dark matter, unobserved matter, whatever. Still no evidence for that, but case in point, Newton is wrong. Like what you learn from Kepler and Newton, like you can't just assume spherical mass distribution and that it just drops off as 1 over r. Experimentally, that's not true. So okay. Like, you can't just treat it as just like a point mass. But okay, let's move on to 5.3 is pretty good too. Okay, we'll quickly go over 5.3 as well, because it's a good problem that helps. So consider a thin uniform circular ring of radius a and mass m, and a mass m is placed in the plane of the ring. So here's the mass m placed in the plane of this ring, and find a position of equilibrium and determine whether it's stable. So dm, so we have like this mass right here, and we have this other mass here, and we want to basically find the position of equilibrium and determine whether or not it's stable. So the potential, right, is just given by the gravitational potential, right, which where d phi is just negative g dm over b. We just took the derivative of phi, where it's phi, right, is negative gm over r. R in this case is b, right, because we take our vector from here to here. And our dm, well, we can solve our dm as, if we use the density is equal to m over 2 pi a, we get gap over b d phi. Okay. With a bit of math, which let me just put up on the screen, since I don't think it's worth me writing in bad handwriting. We can basically allow r and r prime to be position vectors to dm and m right here. So r prime goes to little m, big normal r goes to dm, and then from there we can solve for b. B is just the difference of these two vectors, right, because they make a triangle. And then we can basically solve that in what b is in terms of just getting it in terms of r prime, and we get this function right here. So now we have a function of b in terms of r prime and phi, which is what we want, and then we can integrate that, and we basically get this kind of bad expression, which is very difficult to solve. And as physicists, we're not mathematicians, right? We don't really want to be solving the worst stuff. So why can't we should just expand it, basically, since we assume r prime is much, much less than a, where like basically the mass is pretty close to the center is what we're trying to say, is because we're assuming it's going to be more stable in the center, right? Because intuition tells us if this is uniform, then all these little dm's are going to be like applying a force. I guess the force would be like towards it on the mass. Like, it has all these forces here. So near the center is kind of assumed where the equilibrium point is going to be. And if we expand this under the Taylor expansion, we get equation 5.26, which tells us it's basically proportional to it. That's actually just the definition of Taylor expansion. So anyways, if we plug that in, into our integral, that was just the Taylor expansion. That just tells you what the Taylor expansion is. We plug that in. This is easy to integrate, right? Because it's just basically the integral of cosine. And we get that to first non-zero order, 1 plus 1/4 r prime a squared. And then we can immediately get the potential energy. And let me just screenshot the rest. And we find that the potential energy, basically just multiplying the little mass by the potential, is that. And we can find the equilibrium point, right, by setting the potential energy to 0. So remember, you have like a potential energy graph like that. Equilibrium point is when this is at a minimum. So you can set that equal to 0. And we have to check to make sure the derivative is 0 from calculus. We have to check with the second derivative to make sure it's negative. And that immediately tells us then that the position of equilibrium is this right here. And then using an equation from our earlier chapter to determine the stability, we find that the equilibrium point is unstable. And this is kind of hard to believe, because you would think that if we have a small displacement from the very center, it would just go to, it could just recover back to it, but it's actually unstable because I think it'll oscillate is my guess, I think. So it's unstable. So it will never just find a place and perfectly recover back, unless if there's some non-conservative force at work, which there's not, like air resistance or something. Then it would, oscillate and then drop down to the center. Okay. Now we can move on to another useful equation. You might have seen in a math class, Poisson's equation, which is very useful to compare the properties of gravitational fields with stuff from like electrostatics, which is another class you might have seen this from. So let's consider an arbitrary surface in this figure. Let me just screenshot this figure. So it's an arbitrary surface, and let's see if we can figure out the gravitational flux phi m going through m through some arbitrary surface f. So the flux is given by, again, just like in electrostatics, you want the normal vector, multiply it by g, which is our gravitational vector, right, over the area, dA, right? So if we plug in, we can basically, using the definition of the dot product, right, we know n dot g is equal to negative gm cosine theta over r squared. Notice I drop all the vector stuff because it's a scalar, and theta is just the angle between n and g. This is just normal calculus stuff or vector knowledge. We just plug it into the integral, and we have cosine theta over r squared dA. And then if the integral is over the solid angle of the arbitrary surface, where solid angle is given by basically, how do I describe this? In a system, the solid angle is, it's kind of like, how you go from 0 to 2 pi. Its solid angle is like if you take the entire surface of it, which would be 4 pi, because it's 2 times 2 pi. So that's a bad explanation. I'll have a better one when I revisit it. Sorry about that. But okay, if we look at over an arbitrary surface and has and over the solid angle, you basically get n dot g dA. Well, that's just 4 pi gm. So yes, I'm going to Google solid angle derivation because that's pissing me off. Oops, solid angle. I should know this. Yeah, okay, yeah. So the solid angle is area over r squared. It's like a linear thing. Okay, yeah, here it is. Here it is. In spherical coordinates, it's d omega is equal to sine theta, d theta, d phi. So remember, sine theta, d theta, that gives you a, if you integrate it, 1 minus negative 1 or a 2. And then the d phi gives you a 2 pi. 2 times 2 pi is 4 pi. And that's what happens if you integrate it over a sphere. Okay. And here's kind of another explanation of it in Wikipedia to kind of see what we're physically integrating over. Okay, sorry, that's a little aside, not super relevant, but still important. Okay. So, anyways, let's go back to the problem, or the things we're defining right now. So we can also relate this surface integral to basically if our mass is not just a point mass, negative 4 pi g, we can sum basically over point masses. And if you ever see a sum, notice that's just an integral, right? If you take the limit of it, which is just like infinitely small, rho dv, and we basically recover something interesting using basically Gauss's divergence theorem, because we have a dot is equal to some volume integral. So we have a surface integral is equal to some volume integral. That lets us basically rewrite our surface integral as the divergence of the gravitational potential, the gravitational vector. So, interesting result. And this is where Poisson's equation basically falls out, because we can set the right-hand side of this equal to, so basically we're going to set this equal to this, equal to, what's it called, this 4 pi g rho dv. So we know that these two are now equal, right? Since this is from Gauss's divergence theorem and this is just from math, that lets us write then that the volume integral of negative 4 pi g rho dv has to be equal to the integral volume of the divergence of the gravitational vector. And that means the arguments have to be the same, right? So that means the divergence of the gravitational potential, the gravitational vector, let's call it that, is just equal to 4 pi g rho. Since our surfaces were completely arbitrary, these have to be equal, right? Okay. Now, this is very similar, right, to like, Gauss's law, where the divergence of the electric field is equal to rho over epsilon, different constants, right? And using a, what's it called? Using the fact that the divergence is equal to the negative, just plugging in basically the definition of G as, negative grad phi, we basically get the Laplacian. Laplacian, is that the correct word? I think that's what it's called. The second order gradient, which is, I think, the Laplacian. So we have Poisson's equation now, 4 pi g rho, which is very similar to the one in electrostatics. It is Laplace's equation. Laplace's equation is when this is equal to 0. 0, then Laplace. Otherwise, it's called Poisson's. So it's Poisson's equation. Okay. Very good. That's a good introduction to Poisson's equation. Now we can move on to lines of force and equipotential surfaces. Force and equipotential surfaces. Okay. All right. Let me pause the recording really quick. Is there a way to pause? Okay, I do not know how to pause, so I will not pause it, and I will be back in 1 minute. Sorry about that. I'm recording, 1 second. I'll be on soon. Okay. Let's move on to 5.3. Sorry about the little delay. Lines of force and equipotential surfaces. So we can consider a mass that gives rise to a gravitational field and is described by some field vector g. So we can draw a line outwards from that surface such that the direction of the line at every point is in the same direction of g from that point. And we call that line the line of force. So let's show a diagram and kind of see what we're talking about. So here we have two masses, and we have some arbitrary point P with two different vectors. These lines denote a place where the potential is equal. Along all these lines, like this point and this point, the potentials are the same. Same with this point, and so forth. And it's very useful equation or graphical understanding, because it allows us to kind of view the fact that phi is a constant value on a graph. So if we consider these 2-point masses, this tells us that along those lines, the phi, which is equal to negative gm, factoring out the 1 over r, 1 over r1 plus 1 over r2 is a constant value. Now, why is this concept useful is 5.4. So why do we care? Great, we define this, this fact. So why do we care and where can we use it? Well, let's consider an example. So let's consider a thin uniform disk of mass m and radius a. Find the force on a mass m located along the axis of this disk. So we can approach this by using both a potential and direct force approaches. So let's consider this figure, the differential potential d phi at a distance z. Okay. So we know that d phi is equal to negative g dm over r, and we know that dm is just the area density times dA, which is equal to 2 pi x dx. So some substitution, d phi is equal to negative 2 pi rho g x dx over r, which is equal to negative 2 pi rho g x dx. Now if we look at the distance over here, we have x squared plus z squared is r squared. So our r vector is given by x squared plus z squared to the 1/2, right? So we can immediately integrate, which I will not bore you by writing it out, and I'll just screenshot the actual expression. And we integrate it, and we return this value of negative 2 pi rho g a squared plus z squared to the 1/2 minus z. So from the force form, we resolve the force from the negative gradient of the potential energy, which is just from the scalar function. So we can calculate the force in all directions, but from symmetry we can immediately tell, since it's in the center, all the force components are going to cancel out in every direction except for z where it adds. Stop. Okay, I didn't get my laundry. Shit. Okay, I'll get my laundry in a second. That's fine. Let me just finish this chapter. Sorry about that. Okay, so since we know that it's only in the z direction from symmetry, we can get the force in z direction is equal to negative m d phi in the z direction, depending on z in the z direction, which is just 2 pi m rho g c a squared plus z squared to the 1/2 minus 1, which really simplifies our problem because we only have to do the gradient basically in one direction, since we know the other directions don't matter. Like they cancel out basically, they contribute 0. So in the second method, we basically find that the differential force element is equal to negative gm dm r squared er, and since all horizontal components again cancel, we just need to find the differential element in the z direction, which is cosine theta df, which is just negative g cosine theta dm prime over r squared from the above equation. So if we integrate dm prime is equal to rho 2 pi x dx again, the same way, we can basically obtain the exact same result. And then we see that the two methods are therefore equivalent. Okay, that leads us to the last section, and probably the most interesting, which I'll spend probably the next 10 minutes talking about, is ocean tides. To a very good degree, we can explain how ocean tides work from Newton's formulation. So Newton was the first person to actually try to give an adequate explanation, since Galileo really couldn't account for the timing of it with his math. So we know we have the moon and the earth, right? And the mass, the force on M due to the earth and the moon. So writing down Newton's second law between the two systems, right, is the difference of the gravitational potential energies. And the force on the center of the mass of the earth caused by the moon So that's the force on the moon. Now the force on the Earth is given by basically just the gravitational formula, negative gmm over r squared. So if we look at a diagram of the moon and the Earth, we can see the formulation of this equation. So we have our distance here squared, and then we can kind of resolve what happens at the extremities. So if we look at a polar view of the moon along the z-axis, we see how the moon is inducing a strain at this point and this point, like this, stretching it out from the diagram. But let's see this mathematically as well. So we want to find the acceleration as measured in the non-inertial system at the center of the Earth, right here. So of the moon, of the Earth. So if we subtract the two, we get the non-inertial acceleration. And just plugging in from above, we resolve this equation right here. And we see that the first part is due to the Earth, right? The mass of the Earth also contributes to the tides. And then the moon contributes with this cross term right here. In other words, it's due to the difference between the moon's gravitational pull at the center of the Earth and on the Earth's surface. So the moon pulls here, but it also pulls on like the mass over here a lot more because it's closer than the mass all the way over here. And because of that, it causes an unevenness. And we can resolve the tidal force as just basically the second part, which is just if we multiply this by m. And this right here is our tidal acceleration. Now we can resolve this into components, and we can get the tidal force on the x-axis is given by we remove the ER components and just replace it with a unit vector in the x direction, and we resolve this equation, which doesn't mean much until we can expand it using the 1 over 1 plus x squared expansion, and that resolves us to a much more usable format, which we can do since we know the distance between Earth and the moon is much, much larger than just the radius, right? And that resolves us a much simpler equation where we see a cubic, or 1 over 3, dependence. And then we can do the same thing in the y direction, and we resolve a very similar equation with different factors, but same d cubed expression, which is what we expect to see. So if we look at the Earth again in a nice little diagram, we see the tidal force is acting on both sides like that. In other words, if we approximate the Earth as a sphere, since the ocean water is much more mobile than the other mass that's landlocked, that can expand, and that's what causes the tides. And this is obviously exaggerated and also doesn't help that the Earth isn't an actual sphere, but this allows us to analytically describe how the tidal forces affect, how the moon affects the tides on Earth. So there's other effects as well that cause some problems with Newton's formulation of this, and we have a better formulation of it if we include more factors, but Newton was the first person to actually formulate an actual explanation that was mathematically consistent with the actual timings of the tides. So that's it for chapter 5. So next time we'll be going over chapter 6, which from a quick preview is basically just more math into useful mathematical tricks and stuff like Lagrange equation and Hamiltonian formulation that'll help us. So thank you guys for watching, and I will see you guys in the next video. And sorry about the delays in the middle. Control